stress? Technically, what is the strain means? So what is the stress? It's a pressure actually. So force per unit area is your stress technically. The unit is Newton per meter square or pascals. Or strain is what? It is the extension per unit original length. Or you can say change in length per unit the original length, and it doesn't have any unit. Okay? So I want you to write the definition of both of them. It's just written over there. Then we will come to the graph, which is very, very important topic. And on the basis of that, there are so many conclusions we will get it. Put a heading stress and write the definition. Then put a heading of strain and write the definition. Manur, when is your first exam?
7th May.
10th May. So we have a time.
7th.
Yeah, we have a time because IGCSE examination are just started at the end of this week. So I was thinking might be your examination just started. So we have some time anyway. I was like, Okay. Did you copy stress and strain both?
Yes, sir.
Okay. Now I want you to develop that graph and then we will explain each and everything. Just draw this graph as it is written. I mean, as it is drawn here. Label it and everything, and then we will explain each and every point in this. Okay. Did you?
Sir, I'm done.
You're done. Okay. Now, one by one, we see few things in this. Whenever you apply a force, what we believe is every object has some capabilities. Let's talk about general. Let's talk about a rubber band. My question to you is, when you apply a stress or let's suppose you apply a force, what will happen? What is the first thing you see in a rubber band? Yes, Manu?
It will stretch.
It will stretch. But question is, after you remove the force, will it come back to its original shape or not?
It will.
It will. But if you keep increasing the stress, one time will come up that it will not come back to its original shape, but it will be deformed a bit. Am I right?
Yes.
It means that you reach to the limit of that particular object, and now it's not even coming back to its original shape, even if you remove the force. So every object has that limit, and that limit is called as elastic region. So every object has that elastic region. Within this period of time, if you apply any force, it will come back to its original shape. That is what we called as elastic limit of an object. So now, first of all, I want you to put a heading elastic limit. Elastic limit. Now, what exactly is the elastic limit? Elastic limit is the point till when the stress is applied on an object, the object comes back to its original shape. The object comes back to its original shape after the removal of the force applied. Then put a heading elastic region. Elastic region is an area in which if the stress is applied on an object, if the stress is applied in an area, if the stress is applied, the object will come back to its original position. The object will come back to its original position after the force is removed. After the force is removed. Now, Manur, if you see the graph here, can you see that straight line? The first half? That one?
Yes.
That straight line shows you that you are in elastic limit. You apply stress, and once you remove your stress, the object comes to its original shape. It's linearly expanded. You apply the stress, it gives you a strain. It gives you a strain. You apply the stress, it gives you strain. Once you reach to this point, now if you apply the stress and you remove it after some time, or you stretch it and it won't come back to its original shape once you go beyond this point. Now what happened? It will start deforming. After finishing the elastic limit, your plastic limit starts. Plastic limit means whenever you apply a force, now object will no longer be the same object. It will be a deformed object. So now your object shape is changed and it will be continuously deformed now. After this point, now if you apply a small force, it will be deformed very big. Like the strain goes increasing at this point, even very small force is required after this. So now plastic limit is actually started. And within that limit, what happened? You apply the force more than the elastic limit, the object will be deformed badly. If you increase the force, it will deform, it will deform, it will deform, it will deform until you reach to this point. That is what we call as breaking point. Breaking point means it will be a point where your object will be broken up, finished. So what will happen? The first region will come up as an elastic limit, then a plastic limit, then a breaking point. Okay. So these are the regions which are coming. Now let's see points which are coming here. The first point is called as P point. Now P point is a very interesting point. P means it's a proportionality constant. Till here, till this point, you will always see a direct relationship. When you apply the stress, your strain will be increased. But remember that that particular rule is applied only and only within the elastic limit. That's what the Hooke law is saying. You apply the force and there will be a strain, but that strain and that force will be within the elastic limit. As soon as you reach to point E, now E is a maximum limit point. As soon as you cross that E point, now you can see a small curve which is here. Am I right? This is small curve. Yes, Manu. Can you see that? Small curve.
Yes, sir.
At this point, we called it a yield point. Now, what is yield point? Yield point is a point which is the start of a plastic limit. If you reach till this point, it means now you cross the elastic limit. Now, if you remove the force or force is being removed, you are no longer come back to original position. If it's a, like, for example, if it's a rubber band or something, now it will not come back to the original position. It will definitely will stretch a bit. Even after you remove the force, it will not come back to the original point. After this point, now if you increase the stress, there will be strain, but strain value is going to be increased very much till your point UTS come up. Now remember that UTS doesn't mean it's a breaking point. It's just a limit of a plastic. At this point, this is the maximum deformation a one rubber band or an object can have. Right after UTS, you will have a breaking point limit where the object is now going to be broken down. So this is how we define it. Now I want you to write these things. These points are defined here. The P point is defined here that P is a limit of proportionality. The extension up to this point is elastic and obeys the Hooke's law. The strain is proportional to the applied force. If the strain is relaxed, the wire returns to its starting length. I want you to write about this P as a whole. This is very important, so I want you to write it quickly, please. Now, this is the P point. Now, what is the next point, which actually needs to be explained? That is what we called as the E point. Now, E is the elastic limit. Up to this point, the wire will return to the starting length if the stress is relaxed. However, the graph is curving, so Hooke's law is no longer obeyed. So this is the limit, even though this is the limit, but this is beyond the Hooke's law, that point, because curve is being curved at this point. After that, you have a Y. Y is called the yield point. The wire is now being permanently deformed, and at point Y, there is a sudden increase in the strain, actually accompanied by a reduction in the applied. So, on a very less force after this, strain will increase at this point. And then you will have UTS, which is called ultimate tensile strength. This is not necessarily the breaking point. The wire is deforming plastically. The wire will now continue to stretch with reduced applied force. So basically, this is now we almost reaching to the end of the plastic limit, and the last is the breaking point. So I want you to write all E, Y, UTS, and B, please. Okay. Now, an interesting part which is actually there. If you see this graph, right? If I ask you the gradient of this graph is what? I mean, which value it gives you if you ask, if you have to find out the gradient of the graph?
The Young's modulus.
Young's modulus. So basically, if you, I think you better write in a, star points that a graph of a stress and a strain, I mean, the gradient of graph of a stress and a strain is Young modulus value, which is equal to stress upon strain. Now, if you check on the right hand side, I'm just showing it to you that there are different type of materials having different type of graphs. They're the same things, but they are different type, right? Sometime you have seen, you will not have a, now check this out. The first one is called a brittle one. Brittle means hard one. You will have a directly proportional value. After that, it will break. It will not bend. It will not, there is no plastic limit in there or something. So the graph, I want you to just quickly, don't need to write each and everything. This straight line graph is a brittle material graph. Brittle means a one which is very, very hard. It means that it doesn't have capability to actually go into the plastic limit too much. If you try to mold it or doing something with it, it will break. If you see the second one, that is again a strong material like a steel, it mold to some point. There is a small plastic limit with that, but it will break anyway. If you see a C graph, you can see that yes, it molds and it goes into different region. So it's a ductile, a pure copper. Lack of impurity atoms make it much easier for an atom planes to slide past each other. The D is a simple plastic. There is a big plastic limit in that. So you will have a big value for that. So there are different versions or varieties of stress and strain graph. Okay. And another thing, the graph between force and extension, if you check it out, if you find out this one, it will give you an energy. Remember that. So you can find out the energy by simply find out the area under the curve. So basically, it will give you how much energy which is being lost. Now, few things which is very, very important here. I want you to, it's actually solved here, but I don't want you to see the graph. Just check it out, the question number one. Can you draw a graph, please? Let's do the first question, okay? Can you draw a graph here? And then we will find out few things in this.
For question number one, yes.
Yeah, just question number. There are other questions, but first let's see question number. So there, what's saying is estimate the elastic potential energy. It means that you have to find out the area under the curve, right? So can you find me the area now? Estimate it as a triangle, okay? Try it as a triangle and then solve it and let me know what is the energy coming up. But also remember one, yeah, you can do that because it's in kilo and it's in centimeter, so you do not need to change it. Both will cancel the effect of each other. But I think you better change it. It's always better. So once you do that, the value here is about 60. So it's 60,000 or 60 into 10 to the power 3. And the value at this point is 0.2. So basically 0.2 into 10 to the power minus 2. So length into height divided by 2. What is the value coming up?
It's 6.
6. But why it's coming 60 joules in this? Is it our calculation right or what? Can you recalculate it again, please? Because it looked like 60 to me, not 6. Because if that multiply by that will give you 10 and that 2 and that give you actually 30. 33 to the 6. Yeah, it is 6 actually, technically.
I have 0.6.
0.6. Now the value reduces. Can you solve this? I mean, can you solve that? What is written here in the answer? Right in front of you. What is the calculator showing?
So can you repeat that?
No, I mean this one 0.5 into 0.2 into 10 to the power minus 2 multiplied by 6 into 10 to the power 3. Can you check this out? Is it really 60 or 6? Yes, Manu? Ye- Did you check?
Yes, sir, it's 60.
It's 60. So it means there is a calculation error then. So basically, the first one is your elastic potential. Why? Because you are in elastic range during that region. And when it says heat transfer in the stretching, it means you're talking about this region now, the region which is a bit ahead. Now, how to find the region? I mean, how to find the area for this region? You have to consider this as a trapezium now. So consider it as a trapezium and then solve it. Or you can do it as a rectangle. So this length is how much? Approximately, I mean, wait a second, what he did. They say they did 0.3 into 10 to the power minus 2 somewhere here, and then they multiplied by 65 somewhere here in the middle. So actually what they do, they just take it as approximate value, which is coming as 195. What I am interested in is this one. F is equal to ME is not our thing. So this is not the case. Manu, any problem, any question in this? Or shall we move on?
So where did they get the 65 from?
Which one? Which part you're talking about? This one.
For one, heat, they got 65.
Actually, I really don't understand this, where they get the 65 from, because point 0.3, I think they are taking the average value, because here we got 60, somewhere here we got in the middle. They took the average value. They approximated it. You know, we can't find it exact value because it's a curve. So you have to take some approximate value. If you're considering this as a rectangle, what they did, they are not taking the value 60. They are not taking the value 70. They took the average value, which is coming 65. Same thing, it's zero point 0.2, it's zero point 0.5. So what they did, they take an approximate value. By the way, this is not a course, this is not our part. Our part is EPE, the energy under the, that elastic potential thing. All right.
Yes.
Okay. Now let's move to the further thing, which is important actually. I think we have done this, or I just not remember we have done that. The series one or the parallel one?
We haven't done it.
We haven't done this. Wait, if we didn't do that, then let me just complete it. Okay. I think we didn't do this, so don't. This one we have done, right?
This one, yeah.
Okay. If this one we have done, this one we didn't do. Now, important thing. The formula is F is equal to KE. Sometimes this is F is equal to K delta X, depending upon. But the important thing is, if it's a series, the formula become a sort of a parallel circuit, and you can think of it as you can see the K value actually, rather than, okay, you tell me one thing, the K value will increase or reduce in parallel circuit I'm talking about. Remember that in parallel circuit, the value technically increases because actually it's stretched. I mean, these two are actually attached by the single thing, while in series, it's stretched more. So technically, the total K value will be equal to that. So it will be 1 by KT is equal to 1 by KA plus 1 by KB. So the combination spring constant of a spring A and spring B connected in series is equal to that. So you just need to remember that when it's a series, so the combined effect will be, we can say, divided. KT is equal to K by 2. While in parallel, the effect will be added. So the constant value going increasing. That's the reason the one which is in a parallel one are much more appropriate, because at this point, the K value will be increased and it can handle more pressure, you can say. While here, the K value will be reduced. So when the springs are connected in series, they may not I mean, capable of handling more strong power because it will be stressed on both the springs. While here, it will be stressed on the both of them, but they both will add to give you the total spring constant. While on the series side, it will be simply, you can say that the spring constant will be actually halved of it. So if, for example, you want to hang something, you better go for a parallel spring combination rather than a series spring relationship. So I want you to copy the small theory related to that and the formulas.
So why is the spring constant for a series? It's inverse.
Reason very, yeah, very good question actually. You know, the reason very simple is the series constant when there is a series, right? My question to you is, can I ask you one thing? When you actually put a some strong pressure or some strong machine or something at this point, stress will be actually experienced by both the strings or one spring?
Both.
Both of them. So in that case, actually, the spring value will be weaker because the pressure will be on both of them. So technically, rather than it increases the stuff, it reduces the stuff because one will stretch, will give a stretch on the other one as well. So once the calculation is being done, what we have seen, the spring constant value rather than increasing will be reduced by half if both the springs are same. As far as parallel circuit is concerned of the springs, what we have seen it, when it is stretched, here both are also actually technically, now here both will actually add to give you a double spring constant. Because I can give you an example, even if one spring is broken here, the other one will take the part and one can take the fully responsibility. My question that in series, if one spring is broken, what will happen? Anyone, first one or the second one, what actually will
It
happen?
would all break.
It all breaks. So which one is more beneficial or powerful? The one which is in parallel. So you cannot hang a big, strong weight thing along with the series one. You better always choose the parallel combination. Now, there is nothing actually technically left in this. I believe we better take a look on the past papers. How does they look like? And let's see what is actually a problematic area for you. I mean, you said you have a problem in solving these problems. So, I mean, let's let's address them one by one. What do you say? Shall we do that? Let's start with the latest one which you have just given. Let's discuss some of them and let's see if this is your first. What they're saying is it's a measurements. We come to this in a minute. They say electron is produced during pair production. Describe what happened in the pair production event. So electron is produced during each pair production. Describe what happens in the pair production. So basically electron and positron are actually formed when two gamma rays are actually combined to form electron and positron in the opposite direction. Is it like this?
Yes.
So that is, you have to just write it down. And you have to draw a diagram if you remember that. You know that diagram? I just forgot a bit of the diagram. It's like that, I think. Something like this and something like that. I forgot that. And then they actually combine to give you one electron here and one positron here. That diagram is very much important in this. Okay. Shall we go further?
Yes.
All right. Now, alpha particles were directed towards the gold foil in the Rutherford experiment. Describe the path of the particles. Now, if you remember Rutherford, I have spent one complete unit on this. When you do Rutherford experiment, there are three different paths alpha particles are followed. Once you are bombarded them on a Rutherford, I mean, once you are bombarded them on a gold foil. You know, when there was a gold foil, let me just show you. You bombarded alpha particles on that. There are three paths it will follow. One, they go straight down. One, they deflected with a large angle. And one, they rebound back. One, they go straight down. What is the conclusion for that? I'm just asking
Most of
them.
the nucleus is empty space.
Most of the nucleus is empty state, or you can say hollow. And what if they are actually deflecting with a certain angle?
The nucleus is positively charged.
No, but they are deflected. I'm not saying it's reflect back. They deflect to a certain angle. It
Most of
means
the mass is in the nucleus.
most of the mass in the nucleus, and nucleus is very small. That's what it means. Technically, it means is the mass is in the nucleus and nucleus is very small. That's the reason some of the particles are even deflected with a small angle. And some of the particle, very some of the particle are reflect back. And why they are reflecting back?
Because it's positively charged, the nucleus.
That's it. So you have to just write it down. But they didn't ask for this. They just asked the path of alpha particles. So you have to just write 1, 2, and 3. What are the paths of it? First path is that after you bombard the alpha particle, they go straight down. One is they are deflected to a very small angle, and one they reflect back. Three paths. They didn't ask for any explanation. 3 marks, 3 reasons. Okay. Let's move on. What is the next thing they are asking? Rutherford's scattering experiment was responsible for a change in understanding the structure of atom. Describe the Rutherford model of an atom different from the previous one. Now, what was it? If you remember, the first one was that whole of the atom is positively charged and there are very few electrons which are at different places. Okay. So now the results what came in, they showed that the nucleus is at very small place within the hollow atom and all the atom is empty. Previously, it was but plum and pudding experiment actually, and that shows that everywhere in the atom are positively charged particles and actually electrons are revolving around them and they are very few in numbers. Okay, so for that, actually, I want you to go through this. Actually, these are the one. It's just opening. Just a minute. This is the Brownian motion thermal. This is in very much detail, and I personally like this one. Check it out. Okay, the Rutherford experiment is shown in very much detail in this. If it's opening up, internet is today is quite slow actually. So let's see. Newton's. Okay, there are a few things which are left in this, but we will see. Nucleus, protons, particles, antiparticles, classifications. Interested in this particular classification? No, not this one. This is classifications, energy levels, wave duality, analysis of the matter, conservation. Interesting. Where is that thing gone? Last time I've seen that, and now suddenly again it's gone. But anyway, it's a Rutherford atomic model, what I was actually talking about. Diagram, I've just shown it to you. Can you see the diagram?
Yes.
So see the diagram here, alpha particles are going there. Most of them are going straight down. Very few are reflecting back and some are actually going by some angle. Now, the majority of the alpha particle went straight down. This suggests that atom is mainly empty. Some of the alpha particle deflects to the small angle, less than 10. This suggests there is a positive nucleus at the center, and the only sum of alpha particles deflected straight back. This suggests that nucleus is extremely small, and this is where the mass and the charge atom is connected, concentrated. And this is concluded that atom consists a small, dense, positively charged nucleus. I want you to write these results, and then whenever it comes, you will write in the same way, suggestion and the results. Can you write it, please? Point wise, 1, 2, and 3. These are the 3 points you have to write when this kind of question or this question will come up. Okay. Okay. Now let's see what was it actually. That was a previous one. Since atoms were known to be neutral and the negative electrons were thought to be on a positive sphere of a charge. That is what we called a plum pudding model before the nucleus was theorized. So what it was actually, the electrons are here and very small positive charges are anywhere in the space. Now it is known as the negative electrons are orbiting the nucleus collectively, and these make up the atom. I am giving you a small task here, but actually we do not have time for this. I want you to go through this plum pudding model. Can you write it down? Plum pudding model. This is a small model. I can just give you a small brief on that. That plum pudding model means everywhere in an atom is plus side, plus charges, and electrons are revolving around it. That was a very old model, and Rutherford actually changed the concept of it. So your small task is to just go through what plum pudding model is. Tomorrow, I will ask you what did you study about plum pudding model. Okay, understood?
Yes,
Yes.
sir.
Okay. So we will stop our class 8, and from tomorrow there are we left with two topics now. One, of course, we are continuously working on the past papers, and secondly, we got mechanics left, and we got one projectile motion topic left in this, and one is F is equal to ma1. Which one you want me to start with? Projectile motion or mechanics one, or the one which I just talked about, F is equal to m? Which one you want me to start first? Because we will do the past paper along with that as well, but I have just seen through that we have a mechanics big portion. I think we better start with mechanics. What do you say? So mechanics, shall we go with mechanics then? We will go with the mechanics, plus we will go with the past paper practice. Okay? Tomorrow, inshallah. From tomorrow onwards.
Okay.
So see you
Yeah.
tomorrow on the same time, inshallah. Okay? Just go through the
Sir, do we
yeah.
have class tomorrow or is it on Thursday?
Oh, sorry. I mean Thursday. Sorry. So what you do now,
Yeah.
you start working on the past papers as well and find out the question which you think are difficult. Okay. But your task is to
Okay.
do plum pudding model, and now start doing question relating to the young modulus and all this, and tell me if you find any problematic area. So that we will do that. And then inshallah we will have a class and we will do projectile motion and simple mechanics question. Plus we have a force thing left on there. Okay.
Okay. Yeah.
So see you on Thursday then, inshallah, our next class. Take care.
Yes. Bye, sir.
Bye.